Hello, and welcome to lesson 6.3 on graphing radical functions. Today's a good day. It's Monday, it's MLK Day, it's 25 degrees outside. Oh, it's just nice. It's nice to be inside. We could do some math together. We can graph some radical functions. Oh, it's going to be a good time. It's going to be great. So, let's get into it. This lesson is kind of how to graph radical functions without using a calculator, how to make a nice smooth curve of these functions, how to kind of find points and strategies to do that. For the most part, if you're good on your unit one stuff, parent function transformations, and all that good stuff, you should kind of know how to do this already, but there are going to be maybe some differences from unit one in that the functions are going to start to look a little bit more complicated, and I'm going to talk about how to deal with that. At the top of this paper, I have the four main parent functions you're going to want to know for this lesson: quadratic, cubic, square root, and cube root. We're mostly focusing on the radical functions, square root, cube root, but we are going to be required to graph their inverses. And there's that relationship between cubic and quadratic when you take the inverse of those square root and cube root functions. Let's go ahead and get started. Quick word about graphing expectations is you want at least 3 points. So you're drawing these curves, we want at least 3 points. The more the merrier, right? So if you can find 4 or 5, that'd be beautiful. But 3 points is good. That'll be the minimum. That's kind of like what I'm looking for when I'm grading quiz or grading test. That's what we want, okay? And we want a nice, accurate, smooth curve. Here's a quick example. So like cubic and cube root, right? You'll actually notice that those have the same 3 points like this, right? -1, -1, 0, 0, and 1, 1. And cube root has the exact same 3 points. But the curvature is totally different, right? This one is going like this, whereas this one is going up like that. So careful with that. Make sure the curvature that you draw is like the parent function, yeah? Because who knows, maybe you find 3 points like this, and that's the square root function. If for some reason you draw it like this, and it wasn't supposed to be that, then, well, be careful of that. Key features, if you know your transformations, left, right, up, down, you're going to use translations to find your first point. And two key points on the square root or cube root functions are a square root function has an endpoint 0, 0. And so if we move that left, right, up, down, we'll know where the endpoint transfers. A cube root doesn't end because its domain and range, as you see, are all real numbers, but it does have what's known as an inflection point. And so that inflection point is going to move around based off those same exact kind of transformations. That inflection point is really important because that's where the concavity of the graph is going to change. Remember, concavity is this sort of scooping of the graph, right? It's changing from scooped upwards, right? Scooping upwards to scooping downwards. So pay attention to that. It's not too bad. It's not too hard, but something to look out for. Okay, let's get started. So graphing radical functions, basic. So you're just going to kind of look at the ones that you mostly did in Unit 1. And you're really just looking at, I need to plug in creative points that work well. What do I mean by that? So, okay, well, let me make a table, right? So what does he mean by creative points? Example, suppose you evaluate this function at f of 1, right? You say, well, if you plug in 1, you substitute 1 for x, well, then this would be square root of 2 times 1 minus 1. I'm just replacing the x with a 1, right? But then this gets me square root 2 minus 1. Do you know what the square root of 2 is? I mean, it's irrational. You could estimate it to be 1.414, roughly, and then take off 1, and then maybe you could plot that point. But we're going to avoid that. We're going to try and avoid plotting irrational points if possible. Is it to say that you can't do it? No, I mean, you can. And actually, when you get to conic sections, sometimes we have to. You say, what is a conic section, Mr. Spake? I say, you've heard of the parabola. Have you heard of his friend? the hyperbola. Don't worry about that. We'll get to that towards the end of the year. Anyway, let's avoid graphing irrational values. Let's see if we can find nice values that fit on the graph, that fit on these grid lines that we enjoy. So first thing, what I'm going to do is actually find that endpoint first, because it's a square root curve. I can figure out the where that endpoint is based off the transformations. This 2, this is causing a horizontal compression by a factor of 2 or 1/2, whatever. This 1 is moving down 1. So the only thing that affects that endpoint is the translation down 1. So I do know that I have an endpoint here. It went from the origin, 0, 0, and it moved down 1. So I say, okay, well, then that means the point is 0, -1. And indeed, if I evaluate f of 0, well, then I got root 2 times 0, which is just root 0, which is just 0. And then I'm subtracting 1 from that, which is getting me that -1. So yeah, I mean, you can plug in points, and that's how we're going to find the other 2 points that we need. So I say, well, what could I plug in here that gives me a nice value? I plugged in 1, but I got the square root of 2. I say, well, what can you take the square root of and it look nice? Well, you could take the square root of 0, you get 0. You could take the square root of 1, you get 1. You could take the square root of 4 and get 2. You take the square root of 9, you could take the square root of 16, right? So the question really is, what do you plug into x to make these perfect squares, right? What do you do? I said, well, I plugged in 0 and that worked. What could you make x to plot this, square root of 1? I say square root of 2 times what is 1? Well, 2 times 1/2 is 1. So that's 2 times 1/2 is square root of 1 minus 1. That's just 1 minus 1, which is 0. So if I plug in 1/2, I get 0. Now, I'd really like to avoid fractions. I mean, it's fine. If you're forcibly divisible, it's fine. It's good. And especially 1/2, we can kind of eyeball it. That's about right there, right? That's not so bad. I'm going to strive to find ordered pairs of integers, right? Whole numbers, if I can. And so I say, well, how do I make a 4? Well, I do 2 times 2. So I say square root of 2 times 2 minus 1. That's square root of 4. And square root of 4 is 2. Minus 1 is 1. So when I plug in 2, when I use x as 2, the output is 1. So I say 2 comma 1 is my point right there. And I'm going to just keep on doing this. How could I get a 9? Well, I suppose I could plug in 4.5. So if I want, I could. So I could put 4.5, right? 4.5 is 3. Sorry, I'm just doing this mentally. 3 minus 1 is 2. So about at a 4.5, it's about 2. But again, I would love to just really have 3 ordered pairs of integers. So yes, I get 4.5 and I get 2. But if I do 2 times 8, I get 16. So square root of 16 is 4, and that minus 1 is 3. So when I plug in 8, let's erase that, 8, I get 3. And that's a lot better. I like that. But you can really see the square root curve coming into formation here, right? You say, oh, look at that. Like so. You know what? Let's erase that guy. And we're going to erase these guys here. Okay? So I'm going to just kind of nicely, I want this to be a nice, smooth curve, which as I've said in other videos is always hard to do on this iPad. But there it is. There's my square root curve, and I'm happy. Yay! Woo! From here, can you analyze domain and range? We've done that before. This is just extra practice, right? You know how to read domain and range, but it never hurts to keep doing it, okay? Domain, we read left to right, so start here and go on to the right. This function starts at 0 inclusive, goes on to the right towards infinity. You can choose to write this in inequality notation too. You could say x is greater than or equal to 0. That's the same thing, right? Range, you start at -1. Start at the bottom at -1 and go up to infinity. So say bracket -1 to infinity, which you could also say is y is greater than or equal to -1. Now notice, what I'm going to do here is I'm going to graph f inverse. we had a whole lesson on inverse functions, and so we kind of already have done this. But this is just to really hone in on the idea of swapping and get you really familiar with graphing inverse functions just based off the image of the graph. So if you have that table, I'm going to flip those points, x, comma f of x, f inverse of x. I'm just going to use the pretty points, negative 1, 0, 1, 2, and 3, 8. If you haven't watched the video on inverses, what I'm doing here is every ordered pair x comma y is going to switch and become y comma x. If this is f, then this is f inverse. So the points quite literally flip. And so I'm just flipping the x and y table values. So negative 1, 0 is here. 1, 2 is here. And 3, 8 is here. Oh, no. 3, 8. 3, 8 is right there. Okay? And so I'm going to kind of draw a nice smooth curve. Like so. Smooth. All right. And that's the curve. And you could, again, read this domain and range. Domain starts at negative 1, goes to the right to infinity. Like so. And the range starts at 0. Its baseline is 0, goes up from the axis there. 0, up to infinity. Yay! Woo! And we're done. Right? Okay. And so you'll make an observation here that the domain and range are swapping, right? Right? The domain and range swap. This is just an observation, which we made in the last video as well. If you switch all your x's and y's, I mean, you're switching every element x in the domain with every element in the other one's range, y, right? So naturally, their domain and range swap. Okay. Woo! Let's move on. I'll do one more example here. Let's switch to blue? Why not? Let's switch to blue. Mix it up a little bit. Graph of f of x equals negative 3, blah, 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 blah. Okay, so this negative 3, what does it do? You know what? I'm not going to do all that. The negative 3 does two things. It's a vertical reflection because it's negative. It's also a vertical stretch because 3 is greater than 1. The x minus 4 being inside the radical moves it right 4, and the plus 1 moves it up 1. These all come from function transformations. If you're not sure how I'm doing this or how I'm analyzing this, go back to Unit 1 videos. Hopefully those will help you out. I think it was like 1.2, maybe 1.3. You know, just in case, because it's kind of expected at this point in the year. We've done transformations a few times. We should remember them all the time, yeah? And by the way, you need to know them for pre-cal too. So you have to know them for math going on. Anyway, let's analyze this. So I say, well, this is a cube root function, and it is shifted right 4 up 1. So the inflection point is 4 comma 1. I know this. So I know that I say the inflection, right? The inflection point is 4 comma 1. Yes. And I can make a table values, right? So 1 comma 4. And I'm just going to kind of plug in points, right? What are smart choices of x so that we get values that we can graph? Well, now that it's cube root, right? Cube root of something. Well, we need to do cube root of, what can we take? We take the cube root of 0. And, okay, so we could get that. Oh, why did I say 1, 4? It's 4, 1, silly. 4, 1. So you can take the cube root of 0, which actually happens when you plug in 4. You see 4 minus 4, that gets you 0, so you take the cube root of 0. So that's how that inflection point's coming about. But we could also take the cube root of 1, and we could also take the cube root of 8. Now, don't forget, you can do negatives as well, because a cube root function is defined for all real numbers. The cube root of negative 1 is negative 1. The cube root of negative 8 is negative 2. So these are still values you should be looking for and testing. So I say, okay, well, what can I do? If I want to make the cube root of a 1, I say, what do I minus? Say what number minus 4 is 1? 5. So 5 minus 4 is 1. Cube root of 1 is 1. So it's negative 3 times 1 plus 1. So negative 3 plus 1 is negative 2. So that's negative 2. And I got that by plugging in 5. So 5 comma negative 2. Like right here. Yeah, that's good. That's good. What else can I try? Well, I'd have to do 12 minus 4 to get 8. But this grid only goes up to 10, so I'm going to avoid doing that. Maybe we could find something else. Let's see. I could make a negative 1. I say, what do you subtract from 4 to make negative 1? You can take 3. You say 3 minus 4 is negative 1. So I think I misspoke. It's not what do you subtract from 4. What minus 4 is negative 1? I misspoke there. Anyway, that answer is 3. So when I plug in 3, this is cube root of negative 1, which is negative 1. And negative 3 times negative 1 is 3. Plus 1, because it is plus 1, is 4. So I get 3 comma 4 right here. Now look, that is 3 points. But it might help to have some more if we can find some more. I know we didn't find 12 very well. Also, silly me, look at me. You're graphing all over the right. This is 5 comma negative 2. So I just noticed that I graphed that point wrong. Okay. Yes. So we've got 3 points, but could we find one more? Maybe, to kind of get a little bit better of an idea of what this shape looks like. Can we take the cube root of negative 8? Well, negative 4 minus 4 is negative 8. So if I make that negative 4, I get cube root of negative 8, which is negative 2. Negative 3 times negative 2 is 6, and that plus 1 is 7. So when I plug in negative 4, I get 7. So negative 4 comma 7 is right here. And see, that gives me just, it's only a little bit, but it's just enough to really see a bit more of that curvature, right? Yeah. So I'm gonna flip my iPad over here, and we're gonna, because I always do this, it's easier to draw it like this. So it's gonna kind of come down like this. That's the inflection point right there at 4 comma 1, and then you got to show that concavity changing. Okay, and it goes down like that. All right, nice sketched curve. I've got 4 lovely points on there, and 12 comma something is on there, but our grid didn't go that far to the right, so that's okay. Domain and range, well, that's just all real numbers. Yeah, that's just all real numbers. To find the inverse, I just swap those points, right? So x and then f inverse of x. So you say 1, 4, negative 2, 5, 4, 3, and 7, negative 4. So I say, okay, 1, 4. That's my inflection point. Don't forget it. Negative 2, 5, 4, 3. Am I doing this good? Yeah, I think so. And 7, negative 4. About right there. And this is going to be a cube root function. So it's going to kind of come up from over here, right? And it's going to come on down. And it's going to curve through here, right? And then that concavity is going to change as it goes down this way. I don't like that. 4 comma 3, huh? And negative 2? Yeah, I guess so. Okay, I was just making sure those points are right. Keep that a little bit more flat, and then maybe we'll curve down. Sorry. There we go. Looks a little bit more like that. So maybe this piece It's a little bit more like that. Yeah? I'm just sketching, right? It's just a sketch. You've only got 4 points on here. Okay. And I can see, again, if you swap the domain and range, still all real numbers, which makes sense because for cube, root, and cubic functions, it's always all real numbers. Okay? All right. Not too bad. I've drawn better graphs, but it's not bad. Cool. Let's move on. So that's those two. And at this point in the lesson, this is where I hand it off to you to practice. I'm going to come back and do these problems, but really just if you're watching for the sake of lesson, like, okay, Mr. Spake, teach me, then let me just move on to what I did. So if you want, pause the video and try this one and this one. But I'm going to go ahead and move on to the next new type of thing to watch out for. Okay, switch back to red here. So this says graphing radical functions, advanced. And all this means, it's not really advanced. It's just that it's a little bit more steps, right? You have to kind of clean up the function and then graph it. You see, I gave you this ugly mess, negative 1/3 times the square root of 9x plus 45. Let's manipulate that, yeah? You say, what do you mean, manipulate it? What do you mean? What can I do? Well, look inside that function carefully. You take the square root of 9. You say, there's a 9 in there, Mr. Spake. I could probably pull that 9 out somehow. Now, careful here. You can't just take the square root of 9x plus something. You can't just make that 3x plus 45. Oh, no, heavens. Oh, my gosh. No, do not do that. But what you can do is we have a special property. We have the special property that says the square root of AB is the square root of A times the square root of B. You've been told this since Algebra 1 that this is allowed, and it is. And in fact, the next lesson, we prove it, which is great. 6.4, you prove this property. So you don't have to just take it for Mr. Spake's word. You can verify it for yourself, that it is unequivocally true. Well, as far as we're dealing with real numbers, of course. But yeah, that's radicals. So you say, well, okay, great, but what do you mean? Well, how am I using this? I say, look, y is negative 1/3, the square root, 9x plus 45. Is there anything else? No, that's it. Now, 9x plus 45. 45, 9, special. GCF, factoring, right? I said, well, 45 and 9 could both be divided by 9. So I say this is square root of 9 factored out x plus 5. All I did was greatest common factor, factoring right there, right? 9 would distribute to x to get you 9x. 9 would distribute to 5 to get you 45. I pulled the 9 out. Now, via that property we just talked about, because 9 is multiplying the quantity x plus 5, means you can break it up like this. I say, oh, it's the square root of 9 times the square root of x plus 5. But hey, wait, what's the square root of 9? The square root of 9 is 3. Oh, and negative 1/3 times 3 is negative 1. So the function is negative square root x plus 5. Ah, look at that. Oh my gosh. So much cleaner, right? I would totally rather graph this than that. Yeah. This is just left 5 and vertical reflection. That's all that is. No big deal, right? The other one, oh my gosh, it's like, what? It's like it's vertically reflected, sure, but then it's vertically compressed and yet horizontally compressed. And then, oh my gosh, just too much. Okay, let's graph this guy. We'll make a table, x and f of x. And you'll also see that this is a lot easier to plug numbers into, right? Much easier to just take stuff with 5. So you want to make perfect squares. If I plug in negative 5, of course, I will get 0, which is evident because you're moving it left 5, so the origin moves left 5 by function transformations. But also if you plug in negative 5, you get 0. If you plug in negative 4, you see negative 4 plus 5, that's 1. And the square root of 1 is 1, So the negative square root of 1 is negative 1. So I plug in negative 4, I get negative 1. Negative 4, negative 1. Beautiful. Another creative number. Can I make a 4? I could if I plug in negative 1, right? The negative square root of negative 1 plus 5, that's the negative square root of 4. The square root of 4 is 2, so that's negative 2. So I plug in negative 1, I get negative 2. Negative 1, I get negative 2. Nice. Can we get one more? Could we? I think we could. We could get a 9. You see, I take the square root of, if I plug in 4 for x, 4 plus 5 is 9, square root of 9 is 3. So taking in 4, positive 4, I get out negative 3. 4, negative 3. And there you are. Yeah? A nice upside down square root curve. Like so. Yay! Woohoo! Domain and range. Well, read it left to right, up and down. The leftmost point is at negative 5, and it goes on to the right forever. So it's bracket negative 5 to infinity. The range, you'll notice it extends all the way down to negative infinity. So the bottom piece is coming from negative infinity and is tops off at 0. Yeah? This is the top. It's 0. So bracket. And there it is. Domain range. You'll notice for this one, I didn't ask you to plot the inverse function. Honestly, that's just for extra practice. It's not really the theme of this lesson, but it's just to kind of get the idea that your domain and range switch, and you just flip the points. But yeah, there it is. Okay, I mean, that's pretty much the video. I could probably end it here. I'm not going to, of course. I'm going to do all of them in case you want more help. But I've explained just about everything I need to. So you should have all the tools to be successful on this lesson and the homework. Okay? I will do these other ones, but I know what you're probably waiting for is how to do number 3 on this practice. So I'm going to go ahead and do that one because it's different. Well, it's kind of different from all the other ones. And I'll talk about this one. And then after that, if you're satisfied with the video, click off, but don't forget to subscribe maybe. I don't know. You know that I'm at like 600 something subscribers. If I can reach 1,000, if I can get to 1,000, I could probably monetize this channel. Maybe, as long as I can keep my viewership up. So, hey, consider subscribing. I don't know. Just if you want. Yeah, no obligation. It's okay. You can say subscribe to all your other channels that you like. But who knows? Maybe, just maybe, you'll still be subscribed, and Mr. Spake will be uploading new videos 5 years from now. You'll be in college or something. You'll say, oh, Mr. Spake uploaded something new, right? Man, you could still kind of keep in touch or something. Yeah? Okay. So let's do this one, number 6, or number 3. Graph f of x equals 6 times blah, 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 blah. So this function, I'm going to write it like this, 6 square root 1/9 x plus 1/3 plus 1. How do you do this? Well, you're still going to use factoring, and notice 1/9. You know your perfect squares. 1 squared is 1, 2 squared is 4, 3 squared is 9. Do you know them as reciprocals? 1/2 squared is a half times itself is a fourth. 1/3 squared is 1/9. 1/4 squared is 1/16. Right? So these are our reciprocal squares. If I take the square root of these, well, I'll call it square rootable, meaning I get a value. It's not an integer, but it's a rational number, and that's nice. Yeah? So I can take the square root of these numbers and get rational values here. So because you see a 1/9, we're going to factor out 1/9. 6 root 1/9. And so this will be x. What does the 1/3 become? You think, okay, you're pulling out 1/9, and it's got if you're going distributing back inside, 1/9 times x is 1/9 x. But 1/9 times what is 1/3, right? So, So 1/9 times is 1/3, right? You just got to figure out what that is. Well, we could naturally just solve this if we multiply by 3 on both sides. Or actually, not even. Not even. If we multiply by 9 on both sides, 9 here, 9 here, these 9s cancel, and I get 1 times equals 9/3. Of course, 9/3 is just 3. Oh, that makes sense. Because if I distribute 1/9 to 3, 1/9 times 3, that's just 3/9, which reduces as 1/3. Okay, that makes sense. So factoring out a 9th is kind of like multiplying by 9. It isn't multiplying by 9, but it's kind of like it, right? All right. So we successfully factored out 1/9. Now we can break up these square roots. Square root of 1/9, square root of x plus 3. Of course, square root of 1/9 is 1/3, as we just kind of talked about. And 6 times 1/3 is 2. So it's 2 square root x plus 3 plus 1. And that's the function. Way easier to analyze that, right? That's a vertical stretch by a factor of 2. It's a shift left 3 and up 1. So left 3 up 1 means I could put a point right there for free. That's the end point of my square root function. We'll just plug in points here. -3, 1. If I plug in -2, I get 1. Square root of 1 is 1, times 2 is 2, plus 1 is 3. So -2, 3 is right here. If I'm going too fast for you, pause the video and try to figure out that. I think my hope is that I've modeled this enough that you kind of get it by now, and I can kind of just plug in values mentally. But if you're not sure, just plug them in for yourself, okay? I'll tell you what x values I'm using. Substitute them in the function, make sure it works. 6 plus 3 is 9. So 6 plus 3 squared of 9 is 3. 2 times 3 is 6, plus 1 is 7. So 6, 7 should be another point. And, I skipped 1, silly me. 1 plus 3 is 4, square root of 4 is 2. 2 times 2 is 4, plus 1 is 5. So I skipped that one, whoops. But there we go. Yay! So I got this nice square root curve, like so. Domain, leftmost point is at -3, goes to the right to infinity. Bottommost point is at +1, goes up to infinity. And I'm done. Hooray! That's pretty much the video. So, if you want to take it easy, go on, have fun, go enjoy your rest of your MLK day if you're watching it the second I post this, or whatever day it is that you are observing, or not really observing, but chilling, whatever you're watching this, if it's at lunch or on the bus. Okay, let me go ahead and finish up these last few problems. By the way, there's nothing new here at all. I'm just doing them for the sake of the video. That's it. Okay. Student practice. Let's graph f of x equals square root x plus 1 over 2. Well, this fella, if you go back to Algebra 1, right, x plus 1 over 2 can be rewritten as the square root of 1/2 times x plus 1, right? That's the same thing. Same thing. So that is a horizontal stretch and a shift left 1. So left 1 means it goes right here, -1, 0. Okay? Oh, it just got really quiet in my apartment. There's like no noise at all. It is only me speaking. Okay. Left 1. X, f of x. I can't, it's so quiet. Oh my God. It's like there's no AC. There's nothing. And it's quiet outside too. It's creepy. It's just me, myself, and I. Negative 1, 0 is the first point. Get that free from transformations. What else could I plug in here? Well, notice I'm taking a half of something. So I said, well, what can I take a half of? You want this to be the square root of like 1. So you need to take the half of 2 to get that. So you think, what plus 1 is 2? 1 plus 1 is 2. So plug in 1. 1 plus 1 is 2. Half of 2 is 1. Square root of 1 is 1. So 1, 1 right here. You could maybe get a decimal value if you take half of, like, because I did 4, right? I just did the square root of 4. No, I just did the square root of 1. How do I get 4? I need to take half of 8. So what plus 1 is 8? 7. So 7 plus 1 is 8. Half of 8 is 4. Square root of 4 is 2. Okay, so 7, 2. And there it is. Oh, it's pretty flat, right? It's horizontally stretched. There it is. And that's my square root curve. Starts at negative 1, goes to infinity. Starts at 0, goes up to infinity for domain and range. Flip these points, right? Flip them. 0, negative 1, 1, 1, 2, 7. Plot these. 0, negative 1 is here. 1, 1 is here. And 2, 7 is here. And I'll kind of graph hard with my hand at this angle. It's really steep. Very steep. Okay. Domain just switches. 0 to infinity, negative 1 to infinity. Right? Again, I'm making that observation, right? That the domain becomes the range, and the range becomes the domain. Let's plot one more here. Let's do this in blue. I can rewrite this. So it's 3 plus square root of 5 minus x. That's not usually how we write it for function transformations. 3 plus 5, I mean, that's honestly maybe how I would write it. I mean, I don't care. It's fine. But if you want to analyze it in terms of transformations, you factor out a negative, and so that's x minus 5. And then it's plus 3 at the end here. Okay. Let me erase that square root and make it a little more like that. Yeah. Okay. Ooh, let me shove that plus 3 closer. There it is. Okay. And so this is a horizontal reflection due to the negative outside the x, multiplying x, right? It is a shift right 5, not left 5, as you may have thought before, and up 3. Be careful with this, right? Because it might look like it's negative x plus 5, and plus 5 thinks left 5, but you have to factor the negative out because that's how we write transformations. So right 5 up 3 is right here, like so. So that's the first point for free, x, f of x. I got 5 comma 3. If I plug in 4, 5 minus 4 is 1. Square root of 1 is 1. 3 plus 1 is 4. I get 4, 4. The Wendy's 4 for 4. And then, sadly not sponsored by Wendy's. Wouldn't that be great? Wouldn't it be awesome if I got sponsored by someone? That would be great. I could get in the money, and I could pay for more expo markers. Okay. What else? 5 minus 1. 5 minus 1. I was thinking there. 5 minus 1 is 4. Square root of 4 is 2. 3 plus 2 is 5. So 1 comma 5 is right here. Oh, that's 7. Silly. There's 5. Can I do any more? 5 minus negative 4, but I can't reach that one. So my grid doesn't go that far out. So whatever. That will do. Say, that'll do, pig. That'll do. All right. No, I don't like that curve. Let's curve that a little bit more. At this point, I'm just taking my time and enjoying. Okay, domain left to right, you see it comes from the left at negative infinity, stops on the right at 5. Oh, ugly 5. Oh, ugly bracket. That's better. A little bit better. Still starts at 3 at the bottom and goes up to infinity. And if I switch these points, x with f inverse, swap x and y, 3, 5, 4, 4, 5, 1. So 3, 5, 4, 4, and 5, 1. The endpoint was 5, 3, so 3, 5 is the new endpoint, so it's coming down like this. A little bit better. Here we go. Hey, that's not half bad. Okay, domain from here is 3 to infinity. Range goes all the way down from negative infinity, peaks at 5. And I verify that those domains in range switched. Right? They switched. Right here, this is just for the notes. We are use the fact that, sorry, this doesn't need to be included in the video. If I don't write it there, I'm going to forget before I publish these notes. Okay, 2 more, and then that's the video. But again, look, it's just extra practice. Maybe you're still here. Maybe there's not a single soul is even watching at this point. I don't even know. How would I know? I wouldn't. I guess you could leave me a comment and say, Mr. Spake, I'm watching. I watched the whole thing, Mr. Spake. Okay. Sorry, that's not how anybody sounds like. It's just my interpretation of the general student. Okay. All right, f of x equals 2. We got to clean this up, right? This is a cube root. So we're going to factor out 8. You say, why 8, Mr. Spake? Why 8? Well, it's a perfect cube, right? We're doing cube roots, so we're not looking for perfect squares. So I say, take the cube root of 8 out like this, like so. Yeah? This is just like the one down here where we took out 1/9, right? But it's cube root, so I care about 8, and the cube root of 8 is 2. So it's 2 times 2 times the cube root of x minus 1 plus 2. Of course, 2 times 2 is 4, so it's 4 times the cube root of x minus 1 plus 2. Like that. Okay. Which is right one, so it's a vertical stretch, and it's moved right 1 and up 2. So right 1 up 2 is right here. Okay. Make a table, as I do. Right 1 up 2. Let's plug in some points. Cube root of something minus 1. That's easy. 1 minus 1 is 0. 2 minus 1 is 1. Cube root of 1 is 1. 1 times 4 is 4. 4 plus 2 is 6. So 2, 6. Again, if you're not sure how I'm getting that, plug in 2 to the simplified function. This guy. Just substitute 2 in there and calculate it. If I do negative 1, it's 0. 0 minus 1 is negative 1. Cube root of negative 1 is negative 1. 4 times negative 1 is negative 4. Plus 2 is negative 2. So 0, negative 2 is right here. Can I get any more points? I would need an 8. 9 and negative 7. Ooh. I can technically do negative 7. It kind of fits on here. Negative 7 minus 1 is negative 8. Cube root of negative is negative 2. Negative 8. So negative 2 times 4 is negative 8. Plus 2 is negative 6. So that actually just fits on the graph right there. Just fits. And I can kind of get a good curvature from the graph. Like so. That actually kind of sucks. That is actually kind of poopy. I say, what? Mr. Spake, it was perfect. No, it wasn't. That was not my favorite. Oh, this is hard. I say, oh, come on, you gotta get that concavity in there. Oh, there we go. Ooh, there we go. Okay, it's a little rough in the middle there, but he's better than he started. Maybe smooth him out a little bit there. There we go. Kind of like that. Yeah. Much easier on paper than an iPad, but whatever. Hey, it's the way it works. Domain range is all real numbers, as always, for cube root functions. Easy peasy. Cool. Move on. Next one. Number 2, f of x equals blah, 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 blah. This one's a little tricky with that factoring because it's got a few things going on for itself. You got 12 minus 4x. Yeah, you can factor out 4, but we should also factor out negative. So observe, negative square root 12 minus 4x minus 1. Okay. What we're going to do is we're going to factor out negative 4 from this expression. So negative 4 times x is negative 4x, and negative 4 times negative 3 is positive 12. Okay? Now, here's the thing. You can't pull a negative out of a root. Because if you did, if you said this was square root negative 4 times square root x minus 3, well, square root of negative 4 is 2i. That's an imaginary number, and we can't do that. I mean, I guess we could. I guess there's nobody saying you can't do it, but we can't graph imaginary, so we're not going to. Oh, well, okay, that's a lie too. You can graph imaginary if you graph the real numbers crossed with the complex numbers, the complex plane here, but we're not doing that. We're graphing reals with reals. So we don't want imaginary numbers, right? Right, everybody? So we're just going to take out the 4. And you're going to leave the negative behind. Square root of 4 is 2. So it's negative 2 square root negative x minus 3 minus 1. So got a lot of negatives here. Oh, it's like chock full of them. The negative 2, that is a vertical reflection and a vertical stretch by a factor of 2. The negative on the inside is a horizontal reflection. So we're actually reflecting twice, once vertically and then once horizontally. X minus 3 moves it right 3, and the minus 1 on the outside of the function moves it down 1. A lot of transformations going on here. But right 3 down 1 will tell me the end point, and that'll give me a good starting point for my function. Right 3 down 1, like so. It is probably easiest to deal with this function, to plug in numbers, if I distribute that negative and I say it's 3 minus x. Because then I can mentally figure out what I need to subtract from 3, right? 3 minus 3 is 0. Nice. 3 minus 2 is 1. Square root of 1 is 1 times negative 2 is negative 2. Minus 1 is negative 3. So 2, negative 3. It's right there. To make this positive, though, I can only, if I subtract positive numbers, 3's eventually become negative, and that's not going to be good. So let's plug in negative 1. 3 minus negative 1, that's positive 4. Square root of 4 is 2. 2 times negative 2 is negative 4. Minus 1 is negative 5. So negative 1, comma, negative 5 right there. Can I get any more? 6? Well, we could. We could plug in negative 6. That is 9. Double 3 is 6. Minus 1 is negative 7. Is that right? 3 minus negative 6. That's positive 9. Square root of 9 is 3. 3 times negative 2 is negative 6. Minus 1. Okay, yeah, it's negative 7. So negative 6, negative 7. Wow, it fits on there. Look at that. What a nice function. Oh my gosh. I love her. She's beautiful. Say, this is a beautiful function. Okay. Oh. Okay. Domain and range. Well, domain is coming from the left from negative infinity and stopping at positive 3. The range is coming from the bottom of negative infinity and stopping at a top of negative 1. Like so. I don't like that bracket. Sorry. I'm picky. It's hard to write on the iPad sometimes. And there it is. We did it. Oh my gosh, I'm so happy. I've been meaning to do this video. Sorry for the delay on this. If you're watching this in the current year that I'm filming it, 2024, you might be saying, why do you get lesson 6.4 up? Well, lesson 6.4 was an hour and 20 minutes, right? So I wanted to get that one done early. I was looking at rings this weekend. I said, rings, Mr. Spake, for what? I said, for my wedding. We were looking for wedding bands. I got a ring, and my fiance got a ring with little diamonds, right? Little diamonds. No diamonds for me. I didn't want any. Hers was 3 times as much as mine. So there you go. If mine was X, hers was 3X. Okay. Anyway, there's the video. I hope that was helpful. It's a good day. Go enjoy the rest of your weekend or day or night or morning or whenever you are watching this beautiful video. And I will see you guys next time.